Good evening everybody. So today we will talk about the charge transfer transitions. Charge transfer transitions. Here we will see how the electronic spectrum is, most of the cases are very much dominated by this charge transfer. So, what is that? So, whenever we have a metal ligand system, and in most of these complexes we have the metal ion at the center and different ligands are surrounding this metal ion, and depending upon the nature of this particular metal ion center and the ligands, we can have different charge transfer transitions, where we will see that the intensities, basically those are very much characterized by those intensities, and intensities of these transitions are very high. And we also have seen earlier that the corresponding epsilon max, which is characteristic of these charge transfer transitions, can go up to say 65,000 or 50,000 or sometimes several lakhs of these of mole inverse and centimeter inverse, or liter mole inverse per centimeter inverse. So, in that particular unit we can find out that a very high concentration is not required for these charge transfer transitions. So, we can detect. So, if we can monitor a particular charge transfer band for any metal ligand system, we will find that that particular charge transfer band can be of very much analytical use. And that particular band, that means that that particular lambda max value, we can detect the unknown concentration of the analyte. That means we can go down to a very low concentration for any unknown analyte if that particular analyte can show a charge transfer transition. So, if we are also able to detect the metal ion concentration, so we can detect very nicely the corresponding very low concentration of these metal ions at the level of 10 to the minus 3 to 10 to the minus 4 molar to 10 to the minus 4 molar concentration of these metal ions can be detected by monitoring the corresponding charge transfer band. So, if we see one particular case, that means where we have this particular species, that means metal is bound to the ligand system, and where the metal ion is highly oxidizing, and the ligands which are attached to these metal ions are of different type, that means they are reducing in nature. That means the electron density is basically pushed from the ligand to the metal ion. So, in this particular case, oxidizing, it is highly oxidizing. So, in this particular case, the transfer of charge can take place from the ligand side to the metal side. So, in this particular direction only ligand to metal charge transfer can take place, and we will categorize them that a one particular type of charge transfer. So, here this transfer of charge can take place. So, these particular things we can consider as the corresponding charge transfer bands, and we have to find out where this particular charge transfer band is located, and its corresponding lambda max and epsilon max values can be identified. So, the one important factor for this is the intensity of the color is due to that there is a high probability of these transitions taking place. So, the selection rules, whether it is a Laporte selection rule or spin selection rule, cannot be operative over here. So, it is highly allowed transition, and since the transition is very much allowing, so we get a corresponding high probability of these transitions. That is why we get the corresponding intensity very high, and the molar absorptivity is also very high of several thousands. Because we have seen that for case of DD transitions, the selection rule is basically not allowing all the DD transitions, particularly the transition between involving the d orbital to another d orbital, and which results in a very weak absorption. That is why all the DD transitions we have classified as weak transitions. So, now we can categorize these charge transfer transitions as very strong transitions, and in case of those DD transitions, the epsilon values are pretty low, sometimes in the range of 10 to 20 only, 10 to 20 liter mole inverse centimeter inverse, or sometimes very less. That is why if we want to measure a corresponding DD transitions, we have to go for a very concentrated solution, or sometimes the path length of the cell should be greater than 1, which usually we monitor with 1 centimeter path length, but we can use it for up to 5 centimeter or 10 centimeter path length to get an appreciable epsilon value in the absorbance scale. So, in the first category, what we see that the ligands are responsible for transferring the charge to the metal ion. So, what should be the example, and metal is therefore in the highly oxidizing condition. So, if we consider that manganese center is there, and if we know the number of d electrons present in the manganese, and if this particular one is highly oxidizing, that means the highest possible oxidation state for manganese, where there is no d electron present, which is a D0 system. So, for a D0 system, how we can get that, and if we have surrounding this manganese center, if we have 4 oxygen ligands, that means MnO4, since it is in +7 oxidation state, so overall charge would be minus, and this particular species is present in potassium permanganate, and this potassium permanganate is purple in color, and in the solid state they are also colored, and in solution if we take this particular sample, that means the sample of potassium permanganate which is highly soluble in water, and try to measure the corresponding electronic spectrum, we find the characteristic absorbance related to the lambda max values, and the epsilon max is also pretty high, which will be in the order of several thousands. So, which can be characterized in terms of the corresponding transfer of charge from the oxygen atoms. These oxygen atoms are all behaving as O2 minus, which is reducing in nature, and this manganese center which is in the heptavalent state is 7+ oxidation state, and which will be therefore highly oxidizing. So, as a result we get the corresponding charge transfer transition in the purple region. Similarly, mercuric iodide can also be another example of this type of compound, which is showing the corresponding charge transfer transition, which is brick red in color. So, we see that these colorations are in the visible region and they are highly intense. So, the intensity of these colors basically tells us that a charge transfer transition mechanism is operating between the metal center and the ligand. Similarly, chromium in its +6 oxidation state, that means in chromate CrO4 2 minus, it is present in chromate, chromium present in chromate, and like that of our potassium permanganate, it is surrounded by oxygen atoms, and this is also yellow in color due to DD transitions. So, what we see that in all these cases the metal ions may not possess any kind of d electron. So, these metal ions are devoid of d electrons. So, this metal ion in N plus oxidation state, and if this is a system which is 3D0 or 4D0 or 5D0, which is in the corresponding oxidation state of +6 or +7 like that of chromium and manganese. So, it can very easily accept the corresponding charge density. So, when it is accepting the corresponding charge density, we get a transition from ligand. But if in another case metal is in 0 oxidation state, that means metal has more number of electron compared to this manganese center or the chromium center, or in the low oxidation state 1 plus or 2 plus, what we will see, what we will consider these metal centers as they would be highly reducing. That means they are of different character compared to the previous case, and the ligand which is attached to them, if it can be of oxidizing nature, that means it has some extra electron density which can be utilized for accepting more electron density from the metal center. That means it has some vacant orbital which can accept the electron density from the metal center, and as a result the charge transfer can take place in the opposite direction. Here we see that the corresponding transfer of charge, which is nothing but the electronic charge. So, electronic charge transfer can take place in the opposite direction from the metal to the ligand, and in this particular case we will consider that the charge transfer will take place from metal to the ligand. So, this will be another variety of that charge transfer transition which can be considered completely opposite to that of our system what we have just now we have seen for potassium permanganate or potassium chromate. So, the corresponding lambda max values will be dependent on the color of the system, and the epsilon max values again will also be in the range of several thousands due to the high probability of that charge transfer. So, in this case we can have the iron system in +2 oxidation state, and bipyridine can be the ligand which is the corresponding oxidizing ligand, and the corresponding tris chelate which will be showing the corresponding octahedral compound, and it can be dark red in color. Now, due to simply charge transfer, no DD transition can take place in this particular case, iron in +2 oxidation state. and the intensity of this color, that means the dark red color, is due to only the charge transfer transitions. And in some cases we can also have some underlying weak DD transitions, but it would be very much difficult to detect that very weak DD transition, which is basically overlapping with the corresponding charge transfer transition, which is of very high intensity. Similarly, the detection of iron by thiocyanate anion giving rise to a blood red coloration due to the formation of the corresponding species, where this particular charge transfer can take place. Though this is not in the usual low oxidation state, iron is present in iron 3 plus and NCS is there. So, in this particular case we can have the corresponding charge density from this particular direction or in this particular direction. So, we will find it out and which direction the corresponding charge transfer can take place. So, in which direction basically we will find the corresponding charge transfer, we will see, but in these two cases the epsilon max is very high. So, that basically tells us that we are just dealing with some species where the corresponding complexes are showing the charge transfer species. So, the molecular orbitals which are involved there for these transitions, for these electronic transitions, is possible to have mainly metal D character. So, if we have the corresponding orbitals which are involved for the corresponding transitions, we can have the corresponding transitions known as DD transition or ligand field transition. So, we have the ligand field, and the ligand field is responsible for the splitting of the different D levels. We see that there are 5 d orbitals, and in an octahedral crystal field the 5 d orbitals will be splitted into 2 between the T2G and the EG set, and if the transition is taking place from the T2G set to EG set, we will be considering those as the corresponding DD transitions, and these transitions can also be considered as their ligand field transitions, and the absorption wavelength will be dependent strongly on the ligand field splitting. That means, if the delta O or the delta octahedron is known, we find that depending upon the amount of splitting, that means the amount of separation between these two orbitals, the separation between the DD orbitals will tell us that which particular part of the electronic spectrum will have the corresponding absorption, and as a result we see the corresponding complementary color as the solution color or the solid state color of the corresponding complex. But here the corresponding transition probability integral is not very high, and as a result the corresponding epsilon max values, that molar absorptivity would be less compared to the charge transfer transition. So, looking at the corresponding epsilon max values, we will best simply consider that whether we will have the DD transition or charge transfer transitions. Next we will see that whether the ligand character is involved for any type of electronic transitions. So, when one of the two orbitals has mainly metal character, that means in case of these DD transitions, what we see that both the orbitals from where the electronic charge is getting transferred to the destination orbital, both of them are of metal character. But now if we introduce that we can have the corresponding ligand character, the transition can be called as the corresponding charge transfer transition. And This character is basically modifying the orbital character, the molecular orbital character of this particular orbital, which is responsible for the donor level or the acceptor level, is largely modified by the ligand character in association with the corresponding metal character. So, we have, so far what we are just looking at, that we will have two different types of transitions. So, we can classify the charge transfer transitions into metal to ligand charge transfer transitions, which will be considered as M to L charge transfer, and the ligand to metal charge transfer will be known as LMCT transitions. So, in one case the electronic charge will move from metal orbital to the ligand orbital, or the orbitals having more metal character to the orbital having more ligand character, and in the other case we will have the corresponding transition from the orbitals which are dominated by its ligand character to some other orbital which is of metal character and will be known as ligand to metal charge transfer transitions. So, apart from these transitions, we can also have, in some cases, if we can have metal in two oxidation states. That means one metal is in low oxidation state and another metal ion in the high oxidation state, and if there is some chance of getting the corresponding electronic transitions from one metal orbital which is dominated by the metal character to another metal orbital which is also of the metal character, we will get MMCT, that means metal to metal charge transfer transitions. Similarly, in case of the ligands, if we can have two different types of ligand environments, one is oxidizing and the other is reducing, we can also have ligand to ligand charge transfer transitions. So, apart from these two main types of transitions, we can have two other types of transitions involving purely metal levels as well as purely ligand levels. So, next we will see that this particular case how it is happening. In the first case, where we have the ligand to metal and the metal to ligand charge transfer bands. So, we have different types of ligands, and the ligands, if they are not of single atomic, it can be of multi-atomic, and we can have the different types of electrons present, starting from sigma, sigma star, pi, pi star, and non-bonding molecular orbitals. So, we will see that what are the different types of ligands we can have. So, we can see the corresponding molecular orbital of carbon monoxide. As we all know that carbon monoxide can be a very good ligand to a particular metal system. So, we can have, depending upon the corresponding carbon monoxide ligand, or we can have Cn minus or NCS minus or NCO minus cyanate. So, all these ligands if we can have, and they have the different types of connectivity pattern between the atoms present over there. Also we can have the N3 minus, the azide anion. So, what we see that in case of the azide ion, we can have the corresponding charge on it and the number of lone pair of electrons in it, because we can have 5 plus 1 16 electron system. So, it will be 5 nitrogen into 3 times plus 1 charge. So, is a 16 electron system. So, altogether we can have 8 pairs of electrons, whether they can be the bond pair or the lone pair. So, we will have all these. So, is 3, 4, 5, 6, 7, 8, 6, 7, 8. So, something like this, and we can have the charge also. So, what we see here from this Lewis dot structure of this particular atomic species, multi-atomic species, what we will find that if the one end of these nitrogens, the nitrogen, so they are bonded through say sigma bond, and when the bonding molecular orbital is present as sigma, we can have also the anti-bonding level. Similarly, if the second one in this particular side, we have the pi level as well as the pi star level. So, once a bonding level is formed, immediately we can have the corresponding anti-bonding level, as we can see the corresponding molecular orbital picture, what we find that when these two atomic orbitals AOs are forming molecular orbitals. So, we can have the corresponding molecular orbitals like this. So, if this would be, if this is sigma, the other would be sigma star, and for the two electrons present in these two atomic orbitals, we will have the paired electron in the sigma star level, and this is vacant. So, in most of these cases, the corresponding antibonding levels are vacant, and we will be getting the transition, that means the antibonding level can be considered as the corresponding acceptor level. So, we can have sigma, sigma star, pi, pi star, and this are the corresponding non-bonding electrons. So, we have altogether these 5 types of electrons present in some molecular orbitals. So, we have sigma, sigma star, pi, pi star, and the n. So, if the ligand molecular orbitals are all full, that means we consider that the sigma, pi and n, such as that what we have seen just now in case of the azide anion, and azide is also a very useful and very good ligand which can bind into a monodentate fashion to the metal ion. It can bridge 2 metal centers, it can bridge 3 metal centers, or sometimes it can bridge 4 metal ions. So, if the ligand molecular orbitals are full, charge transfer may occur from the ligand molecular orbitals to the empty or partially filled metal d orbitals. So, if these orbitals present, if they can be utilized for the donation, then the metal orbitals which can be vacant over there and which can accept the electron density to its d orbitals, then we will see the ligand to metal charge transfer transition. So, in absorption that is forming from the process of this type, that means ligand to metal charge transfer is taking place, and we will be getting the corresponding bands at LMCT bands. And LMCT transitions result in intense bands, since the probability is very high for these transitions compared to the forbidden DD transitions, and the forbidden DD transition may also take place, giving rise to weak absorptions. So, at the same time, under the envelope of this LMCT transition or LMCT band, sometimes we also find the DD transitions are also there and which are within the corresponding charge transfer band. So, we have the corresponding ligand to metal charge transfer transition, and which is very common for coordination compounds having pi acceptor ligands. So, one important thing what we are now defining, that if we have a pi acceptor ligand, so pi acceptor ligand, that means the corresponding system will have the pi level as well as pi star level, and if the pi star level is empty and it is the corresponding vacant molecular orbital, then we can have the corresponding system where this electron density is not going from there, but this is full. So, in the typical molecular system of the ligand, so if this is the ligand, and within that particular ligand system, when no metal is present, that means no complex has been formed. So, when no metal is present, what we see that in the UV visible range, UV visible spectrum, in the UV visible range of the spectrum, we will see one transition which is can be pi to pi star transition. But when metal d orbital is coming into the picture, we will see that this particular pi electron density, that means what we can accept electron density from the ligand during the coordination, it can donate the electron density, and we can see that ligand to metal charge transfer transition can take place. So, this electronic charge from the ligand level, which is pi, can go to not to the pi star level, but also can go to some intermediate level which is of d character from the metal ion. So, if we have the pi acceptor ligands to us, then what we will see that we have the D6 system, which is the free ion system, where we have so many d electrons available on the metal ion. Then we have the ligand sigma orbitals. So, as we are talking, as it can be the corresponding pi acceptor ligand, but it can also be the corresponding sigma orbitals. So, you can have the corresponding levels, that means the ligand sigma orbitals are there, which are all full, and we can have the during the formation of this complex, this orbital, the sigma orbitals, the ligand sigma orbitals can be of low lying, and it can be the corresponding level where from the electronic charge can be donated to the empty Eg level. So, we have these 6 electrons distributed throughout all 5 d orbitals, which can be cobalt 3. So, in case of cobalt 3, when we have the corresponding crystal field splitting in the system, so the crystal field splitting can gives us one T2G level and another Eg level, and in this particular case the Eg level is empty. So, the cobalt in the trivalent state can show some amount of ligand to metal charge transfer, because the cobalt is the oxidizing one, and if the ligand is the reducing one, and the ligand can have the sufficient charge density, electronic charge density, which can be donated to the vacant antibonding level of the metal ion. So, Eg is the corresponding antibonding level compared to this the T2G level, and which is empty and which is vacant. So, the charge density can be flown from this ligand orbitals to the metal orbitals which are vacant. So, ligand to metal charge transfer transition can take place here. So, we have the corresponding ligand to metal charge transfer involving an octahedral D6 complex. So, in case of octahedral D6 complex, which is definitely of low spin, we see the corresponding transfer like this, and obviously this for this particular case we can have the corresponding separation, which will tell us that which particular wavelength we can see the corresponding transition, and experimentally we can measure the corresponding intensity. So, it is the transfer which basically results in a reduction of the metal center, because some amount of charge is being pushed to the metal ion orbital. That means the partial movement of the charge is going to the metal orbital, that means metal is accepting the electronic charge, that means metal is getting partially reduced. So, at a even higher energy are the LMCT which involve pi donor ligands. So, just now we have seen about the pi acceptor, but if we can have the pi donor ligands around the metal, these transitions can also take place because of the low lying ligand orbitals. So, if we have low lying ligand orbitals like the sigma, we can have also the pi donor ligands which are of low energy compared to the metal d orbitals. So, a transition from the orbitals that are of ligand in character to orbitals that are more metal in character. So, we will have the transition from one center, that means one molecular orbital which is of ligand character to another molecular orbital which is of metal character. Then we will consider the transition would be LMCT. So, the electron basically travels from a bonding pi to non-bonding pi orbitals into a sigma star orbital. So, electron can move from a bonding pi or non-bonding pi, that means pi to pi star orbital to a sigma star orbital which is of higher energy, and these transitions are very strong and appear very intensely colored in the absorption spectrum, and the molar extinction coefficient for these transitions are around 10 to the power 4 or sometimes 5 or 6.5 into 10 to the power 4. That means they are of several thousands only. So, this particular case, so the metal will be the sigma star, metal is giving the sigma star orbital and the ligand is giving the corresponding pi and the pi star level, and whatever we have, that means the corresponding level which we can designate as the Eg, but this can be considered as the corresponding sigma star level, and we can have the corresponding metal. In this particular level we can have the T2G which is not interacting with the ligand, which is remaining as the corresponding non-bonding level for this 3D6 system, and we can have the corresponding pi star as well as pi level. So, either from these two, if both of them are full, that means if the pi level as well as pi star level of the ligand is full, so we can have the corresponding electronic charge transfer from this level to this level or this level to the Eg level. So, this basically gives us the corresponding transitions which would be of LMCT type. So, the examples of these, basically examples of these pi donor ligands would be simply having the pi electron density, that fluoride, chloride, bromide, iodide, which are in the lower end of the spectrochemical series, and they basically sometime in a typical coordination environment such as that of tetrahedral coordination to the metal center, including the NCS and NCO, they can give rise to the corresponding charge transfer transitions to giving rise the corresponding useful ligand to metal charge transfers. So, what we see that apart from these transitions, that means we can have the chromium in +3 oxidation state. One chloride is there, so it is chromium in +3 oxidation state, which is a 3D3 system, and we can have two distinct DD transitions. One is close to say 550 nanometer, another is close to 400 nanometer. And what we will see next, that if we can systematically analyze that what are the different types of electronic spectra we can have, we will find that we can have 3 different types of DD transitions which are allowed into some extent depending upon the corresponding relaxation of the rules, the corresponding selection rules. We will find that the third transition is under the envelope of LMCT transition. Since it is in the log E scale, so we will find that the corresponding epsilon is in the range of 10 to the power 4 for the corresponding charge transfer transitions, which are highly intense compared to these DD transitions. So, sometimes using the same solution we cannot observe the corresponding transitions both in this particular wavelengths as well as this particular one which is close to 250 nanometer. So, for this solution we have to dilute it to 10 times and then we measure the corresponding absorbance at this particular value. So, we are not getting the corresponding DD transitions of the third type, that means which is here, maybe here the third transition energetically if we calculate it out. So, theoretically we can predict these particular DD transitions from some of these diagrams. Basically we will talk about the corresponding coupling scheme and the corresponding diagrams which have a special name for that, and theoretically we can find out the corresponding transitions. So, that particular transitions will be governed by a special type of diagrams which is proposed by these two persons, the Tanabe and Sugano, and that is why they are known as Tanabe-Sugano diagrams. So, these diagrams can be utilized to determine the corresponding transitions what we see in the spectrum. So, in the spectrum we get two DD transitions, and if we typically analyze the Tanabe-Sugano diagrams for D3 system, we will find out that another permissible transition is possible and will be there at this particular range which is in the closed envelope of the LMCT transitions. So, that not only theoretically justify the presence of the third spectrum, but also it can identify the range of the corresponding wavelength for the corresponding ligand to metal charge transfer transition. So, we will now just go for the different term symbols for these different electronic states. So, we can have several electronic states and these electronic states are responsible for these transitions, and for those states we can have some thing we will call them as the different terms for multi-electronic system. When more than one electron is present in different orbitals, we consider them as multi-electronic system, and that particular multi-electronic system will be utilized for finding out the different term symbols. So, one such term symbols how we get, because in quantum mechanics the corresponding coupling scheme is known as the corresponding Russell-Saunders coupling, and due to that coupling a term symbol is an corresponding abbreviated form of the description of the angular momentum quantum number in a multi-electron system. So, if we have 2 p electron or 2 d electron, we can have the corresponding description for the total angular momentum. So, how we find out the total angular momentum of the system for a multi-electronic system, and how we also define the corresponding spin values that can be known from this particular type of coupling scheme which is known as RS coupling or LS coupling. So, we will define the term symbol in the form of twice S plus 1, S is the total spin value and L value and the corresponding J value which is coming from the corresponding coupling scheme between L and S. So, this particular coupling scheme what is known as the Russell-Saunders coupling in this coupling what we will find is that corresponding ml values for a multi-electronic system is summation over the individual ml values, the individual orbital angular momentum values gives us the total orbital angular momentum. In a similar fashion, when we talk about the corresponding spin value, the total spin, which is also sum over the individual ms values, giving rise to total spin angular momentum. So, that gives us the total spin angular momentum. So, if we have the 2p electron system, if we have 2p electron and in a particular electronic state we can have like D2, we can have the p2 electronic configuration such as that of we have the D2 electronic configuration. So, in the simplest possible case, if we have a p2 electronic configuration, since it is a 2p electron, the n value equal to 2, since it is p, the L value will be equal to 1. So, we can have 3 different ml values. ml values can be plus 1, 0 or minus 1, and ms values can be plus half or minus half. So, these are the different possibilities for a 2p electron. So, whenever we have one electron, the first electron having ml is equal to plus 1 and ms is equal to plus half, we will be considering this particular thing as 1 plus. 1 is designating as the corresponding value of ml and ms is equal to plus half. Similarly, for the second electron, if we take ml is equal to 0 or ms is equal to minus half, we will have 0 minus. So, this is a corresponding state where 2 electrons we can classify them by this abbreviated labeling 1 plus 0 minus, where the first one is for the first electron. So, this is for the first electron and this is for the second electron. So, we have the corresponding values for these particular cases where we can have a one particular state which is characterized by the corresponding Russell-Saunders coupled one. Now, we know that ml value and ms values. So, we can have the total S value and we can have the corresponding twice S plus 1 L and the J value. So, this will how we can designate these values for the corresponding states. So, where S would be the total spin quantum number and 2s plus 1 the spin multiplicity, that means the different possibility, the maximum number of different possible states of J for a given L and S combination. So, how many different types of J can be formed, that can also be known from the corresponding 2s plus 1 type of spin multiplicity, and J is the total angular momentum quantum number and L is the total orbital quantum number in spectroscopic notation. So, if we have S value equal to 1, the corresponding multiplicity would be 2 into 1 plus 1. So, 2 plus 1 is equal to 3 is equal to 3. So, that means it will be the 3, and if we have the corresponding value for L, which is 0 for S, P, D and F all other values. So, we can have the corresponding value for the whether it is a 3D term or 3F term. So, we will have the nomenclature for S, P, D and F is derived from the characteristic of the spectroscopic lines corresponding to the small s, p, d, f, which originally assigned for the corresponding atomic spectrum for the different orbitals, that is sharp, principal, diffuse and fundamental, but still we use these 4 nomenclature for L value equal to 0, L value equal to 1, L value equal to 2 and L value equal to 3. So, for a given electronic configuration, the combination of an S value and an L value is called a term. So, how we can have a particular term value which have a one particular S value and one particular L value and has a statistical weight, that is the number of possible microstates, and the number of possible microstates are known from 2S plus 1 into 2L plus 1. So, if we have this value and if we have the L value which is giving rise to twice L plus 1 multiplied by this one, we will get the total number of possible microstates. That gives us the different possible microstates to us. So, a combination of S, L and J is called a level. So, what type of combination we will be looking for? When we have the value for S and value for L, we call it as a term, but when we level it with the corresponding J value, because the J can have the different values depending upon one single value for L and S, we get the level. A given level has again a statistical weightage of 2J plus 1, which is the number of possible microstates associated with this level in the corresponding term. So, if we have one particular J value such as J is equal to 1, we can have 2 into 1 plus 1, that means 3 different levels for the J values. So, altogether all these combinations, that means L value, S value, J value and the J values determines a particular state. So, how we find this particular state from this particular type of coupling. So, if we see that the splitting of the terms for the D2 ion in several point groups. So, what are the terms we can have for a D2 ion and the different of its terms in the different point groups. So, the free ion terms basically we can find out for the D2 ion is 3F, 1D, 3P, 1G and 1S. So, these are the possible free ion terms, and depending upon its L value and the S value, we have the ground state value is of 3F. So, for D2 and its corresponding whole equivalent D8, we can have same number of or same level of the corresponding free ion terms. And if we put these free ion terms in different point groups, basically there will be splitting of these terms, and these splitting of terms will give the corresponding states, and these states are responsible for the individual electronic transitions. So, when this 3F level is placed inside an octahedral field, the 3F level will be splitted into 3A2G, 3T1G and 3T2G levels, and these levels basically are important for the corresponding transitions if we consider that this ground 3F level is defining us that one particular state in weak field, that means a weak crystal field, and this particular strength it can have the 3T2G as the ground state, and that 3T2G ground state will give rise to the corresponding transition from 3T2G to 3T1G or 3T2G to 3A2G. So, after splitting, one will be the ground state and others will be the corresponding excited states. Similarly, for the singlet state where S is equal to 0, we have the 1D level, and like the splitting of the D level, we have the splitted forms as EG and T2G. Similarly, 3P will be converted to only 3T1G. G will be converted to these 4, and this will be converted to the corresponding value for the 1s term. And these values basically can give rise to the corresponding values for these different techniques, where we can find it out that these are the corresponding spectroscopic terms, and among these spectroscopic terms we can have the corresponding transitions. So, how we see these transitions involving the 3p level from here and the 3f level as in the ground state. So, in this particular case we have the corresponding diagram, which we can, very basic one, we can consider it as the corresponding organ diagram, and in the final form it can be considered as the corresponding Tanabe-Sugano diagram. And in that particular diagram, in the Tanabe-Sugano diagram, what we can have, depending upon the corresponding this x axis, how we move this x axis, the x axis is moved from the corresponding change in the corresponding crystal field strength. As we increase the crystal field strength from left to right, the corresponding energy for this particular term is also changing, and we have the energy of these different states in this particular axis. That means the 3p is the ground state compared to the 3p state. So, when we have this 3f level splitted between 3t1g, 3t2g and 3a1g, we have these corresponding levels for the different transitions, and we have the separation between these two as 3p and 3p as the corresponding value for the 15b, which we will see how we plot in the corresponding Tanabe-Sugano diagram for these different values. So, right now what we see that these two values are basically equal to 8 dq corresponding to 10 dq in the crystal field splitting, and these two values between 3t2g to 3a2g is equal to 12 dq. And from these basically compared to this level, that means the unsplitted 3f level, will find out this as a magnitude of 2 dq, which is different from the total 8 dq value. So, these transitions from these levels basically corresponds to some transitions. If we see that for one such transition like that of the Tanabe-Sugano diagram, that we will find that how we can plot these values, and we can have for D3, basically for D3 metal ion we can get these particular levels. So, one is the corresponding splitting for these levels is 4A2, then 4T2 and 4T1. So, from this ground level term we have 3 splitted levels, and from the other excited levels we have the corresponding terms which is originating from the free ion term. So, here on the left hand side we have the free ion term, and basically this diagram is giving us a particular type of correlation diagram, and this particular correlation diagram is useful to find out the corresponding types of the electronic transitions what is involving what particular state from here to there. So, this is the corresponding state where we have the ground state is 4A2. So, for any D3 metal ion, it can be chromium 3 plus, we have the corresponding ground state term as 4A2, and there we will find that from 4A2 we have the all other corresponding transitions. So, this is because of the 3 unpaired electrons we have, the twice s plus 1 what we will find these values in the term, the magnitude of this twice s plus 1. So, since this particular value is there, so we have the corresponding value equal to 4. So, this particular diagram will just again continue in our next class. Thank you very much.